Radio Year 11, here we are. This is the second video for this exercise. We're going to do a few different things in this, but first of all, we're going to solve an inequation given a graph. Now, we have just looked at the previous exercise solving a quadratic inequation by drawing the graph. Now, this, well, we're going to assume you've been given the graph. It might be a more complicated function, but hey, we've already got the graph. It's easy enough to inspect that and see where it is greater than or less than or greater than or equal to, right? To equal to 0. We're looking for when it is above or below the x-axis, according to the conditions given to us in the inequation. So for a here, right, let's write a nice neat a, I'm looking for when y is less than, but not equal to, strictly less than 0. Now here at a, it's not less than 0, but it's close. And here at b, it is close, but not less. And here at c, now at d there, we never get less than 0 anywhere around there, there's nothing below. But between a and b here, right, where a is less than x is less than b, right, between a and b, not equal to, but between a and b, x is less than 0. And also between b and c. Okay, so for b is less than x is less than c. All right. So that is the answer to part A. When is y less than 0 for this function? Right, between a and b and c. Now for part B here, I want to know when it is greater than or equal to 0. Okay, now it's greater than 0 here, this is where it's positive, but also I'm happy enough where it's equal to 0. Okay, anywhere where it's equal to 0. Well, in fact, I don't know. Ooh, whoa, what's happening there? Okay, so that part and this part here. Now, I don't need to worry about a break here because it can be 0 there, right? So I'm just going to say anything greater than c is going to be greater than or equal to 0. So, here, when x is less than or equal to a is one of the solutions. Where x is equal to b is another solution. Where x is greater than or equal to c is the third part. Okay, so we can sort of see there are kind of three disjoint regions here. There's this part here, there's that little point there, and there's this bit here. That's the solution to B, right? You've got the graph. All you need to do really is to inspect it and see where it's above and where it's below. Now, this here is a good example of a continuous function, or at least it is over that domain, right, from here to here. Because I could trace the entire line, cover all of it without taking my pen off. Right? There's no jumps or breaks or gaps. It's called a continuous function. Mostly what we're interested in. A rectangular hyperbola is a good example of a function that is discontinuous. Okay, but we're mostly interested in continuous functions. Sorry for the minor disruption there. So continuous functions, you can draw the whole lot without taking your pen off. A rectangular hyperbola is a good example of a function that is discontinuous. Okay, mostly we're interested in continuous functions. Now there is this thing called the intermediate value theorem. Now that says that for a continuous function, the sign, right, that's whether it's positive or negative. For a continuous function, the sign of the function doesn't change between consecutive zeros. Okay, so if I've got two roots of that equation that are next to each other, right, with a gap in between, if it's positive anywhere between those two zeros, it's positive everywhere between those two zeros. If it's negative somewhere, it's negative everywhere. Okay, it can't go from positive to negative without having a 0, without crossing the x-axis somewhere. Okay, so that's helpful. It means that we don't have to draw too many points, I suppose. So, we're going to find some intercepts, and then we're just going to have a look to see where it's positive and where it's negative with a table of values. Right, we're going to do that, and then we're going to sketch this, well, I suppose, this fairly complicated looking function. Right, now, word of warning, if you have a discontinuous function like, I don't know, rectangular hyperbola, then you have to check the values on either side of the zeros, but also either side of the discontinuity. Right, anywhere where there's that jump or break or gap. You have to check either side of that as well to work out the sign, see what's sort of roughly going on. Now, first of all, 7a, we need the 0. So, first of all, let x equal 0, and therefore y is equal to 1, times negative 1 squared, which is equal to 1. Okay, so there's one of my zeros. X equals 0, y equals 1. My vertical axis. Now, let y equal 0. Therefore, x plus 1, x minus 1 all squared equals 0. Therefore, x plus 1 equals 0, or x minus 1 equals 0. Therefore, x equals negative 1, or x equals 1. Righto, so now I have 3 zeros here. At x equals, right, so in fact, sorry, I have 2 zeros here, and x equals negative 1 and x equals 1. So, my 2 roots here. This is sort of a 0, but it's 0 on the vertical axis, and I'm not too fussed about that because that doesn't tell me what the sign of the function is, and that's not really what I'm interested in when I'm dealing with an inequation. So, what we're going to do is draw up a table of values. Now, I need to be in between these 2 roots and also on either side of them. So, we're going to have x and y, and I'm going to go for negative 2, 0, and 2. Okay, so that's going to be, so if we think of these numbers on number line, I'm going to be here, smaller than the smallest root, here, in between the roots, and larger than the largest root. Right, so a good old-fashioned table of values that we all know and love. Right, let's punch these values into this equation. So negative 2 plus 1, negative 1. So this is going to be negative 1 times negative 3 squared is 9. Negative 1 times 9 is negative 9. Okay, so to the left of this root, my function is negative, right? It's below the x-axis. When x equals 0, in fact we've already seen that, y equals 1, so then it becomes positive, so it goes from negative to positive. That's pretty common. Now, when x equals 2, what happens? 2 plus 1 equals 3. 2 minus 1 is 1. 1 squared is 1. I get a 3. So it goes from negative to positive again. What's going on there? Well, I think we will see something reasonably familiar. So, I love drawing the graph first and then putting the axes in afterwards. That doesn't really work properly for these sorts of things. So here, x and y. Now, we said I have roots at negative 1. Now we know that at x equals 0, it crosses up here at 1. So we'll call that negative 1. 1 and at 1. Okay, now it goes from negative down here. So to the left of negative 1, it's negative. And there's no other roots there, so that just goes down there, that's fine. Now, at 0, it's positive. And then, back here, I know it's got to go down to 0 here, but it's positive on either side of that. So what's happening is, we get this sort of a thing going on, right? It comes down, but it doesn't cross over. It gets all the way down to 0 and doesn't cross over. You often get that where you see a squared like that. Okay? So, this is part A. This is part B, and this is part C, right, with all of our roots and everything else, and that's going to do us for this video. Wonderful. Thanks very much, guys. I'll see you in class.